Welcome back, everyone. So, in the previous lecture, we looked at the various ways that we can use Boltzmann statistics to generate or calculate equilibrium thermal averages of various thermodynamic quantities, which in turn allows us to think or to calculate things like average velocities, and so on. What we're going to look at today is seeing if we can continue to connect the quantum statistical mechanics of Boltzmann back to classical classical thermodynamics. In particular, we're going to look at the Helmholtz free energy. So the Helmholtz free energy again is defined as the thermal energy minus this factor Ts, which is the energy or the heat available from the environment. And indeed, from the thermodynamic identity, we can get a relationship between the Helmholtz free energy as the partial derivative of F with respect to T, holding the volume and number of particles constant, is minus the entropy. If we solve this equation over here for this minus entropy term, so if we solve this for minus S, what we get is that F minus the internal energy divided by the temperature is minus S, which we also said is dF dt, the partial derivative of free energy with respect to temperature. So in other words, that gives us dF dt equals F minus U over T. And this is a partial differential equation for F of T. All right, so in time-honored tradition, the best way to solve a partial differential equation is to know the answer. And we're going to apply that tradition right here. But let's go ahead and motivate the good guess, and then we're going to show that we can use that good guess, and that if we plug it into the equation here, our partial differential equation, it will turn out to be a solution. So let's go back to thinking about what the free energy is, and in particular how we used it. So we used the free energy in the context of a system of some sort, which was contained within a much larger environment. Ooh, our camera is freaking out here. Hang on. So our system was contained in a much larger environment and was allowed to exchange heat with that environment. We were allowed to exchange energy with that environment, but we were not allowing particle exchange. And the environment, the thermal bath, is much, much, much larger, and so it will be held at a constant temperature. And our system will remain in thermal equilibrium with its environment. And in this context, what we found was that while the entropy of the whole universe tended to want to maximize and increase, that meant that at the same time the Helmholtz free energy of our system wanted to minimize or decrease. Right, so entropy wants to maximize, free energy wants to minimize. Well, we know that entropy is a quantity, Boltzmann's constant times the logarithm of the multiplicity, the logarithm of the total number of ways that you can arrange a particular macro state. Well, we have another quantity which is something like the total number of available states, which is our partition function. We said our partition function z was also something like the total number of available states. So maybe log z is something interesting, and in particular, maybe log z has something to do with our free energy. If we want log z to minimize as, or if we want this thing to minimize as multiplicity maximizes, then we better have maybe minus log z. And also, if it's going to be a free energy, it needs to have energy of units. So let's call our guess f tilde. We'll put a tilde on top to remind ourselves that this is our guess, but we'll say it's negative kT will give it units of energy. That's a nice, good guess for a thermal constant that gives us units of energy, times the logarithm of our partition function. So this is going to be our completely out of thin air guess, motivated by some notion that we're making an entropy-like quantity, but building it into something with units of energy. All right, well, then how do we show that this is a solution to our partial differential equation? Well, we shove this into our partial differential equation and start evaluating it. So in particular, that derivative, we would have to evaluate then df dt. Well, that's going to be d by dt of minus kt logarithm of the partition function. Kt, well, so this is a product rule because both the partition function and t are functions of t. So we can do first times the derivative of the second, so that's going to be minus kt times d by dt of log z, and plus the second, which in this case is, or minus log z, that's our second term here, so minus log z times the derivative of our first term, kt. So the derivative of this is just going to give us a k, so this is going to be equal to minus kt d by dt of log z, and then this is going to just be minus k log of the partition function. All right, so d by dt of log z is, by the product rule for derivatives here, d beta dt times d by d beta of log z. And so we're trying to evaluate this little bit right here. So this first term, d beta dt, that's just d by dt of 1 over kt. And the second term, d by d beta of log z, well, that's going to be 1 over z times dz d beta. And so that's going to equal, this is going to give us a minus 1 over kt squared times 1 over z dz d beta, and minus 1 over z dz d beta, that's our energy, over kt squared. So this term here turns into energy over kt squared. And so going back to evaluating our derivative here, so df tilde dt, so going back to this step over here, is going to be minus kt times this thing we just calculated, u over kt squared, and then also minus k log of z. And there's some simplifying we can do here. So we can cancel the k's, we can cancel one of the t's on the bottom with the t on the top, and this gives us energy over t here. And on the right, minus k log t, well, minus k log t, that's f prime, or f tilde, or whoops, so minus, or plus f tilde over temperature. And oh, we forgot our minus sign there. So then df tilde dt evaluates to f tilde minus thermal energy over temperature, and lo and behold, that is indeed the differential equation we were trying to say this is a solution for. So yes, evaluate if this is the functional form of the Helmholtz free energy in terms of the partition function, then plugging it into this differential equation would in fact give us that. Now, it's a differential equation, and so there's always the possibility of that we've lost some dangling constants somewhere. So we need to check versus some sort of an initial condition. And the initial condition we're going to check against is, does our solution at temperature approaching 0 match the actual behavior of the Helmholtz free energy when temperature approaches 0? Well, so what is the behavior of the actual Helmholtz free energy when we approach absolute 0? Well, if the Helmholtz free energy is thermal energy minus the heat available in the environment, as the temperature goes to 0, obviously this second term is going to go to 0. And this first term, well, it might not be able to go to 0. Indeed, there's probably some non-zero energy which corresponds to the energy of the lowest state of our system. And so the behavior of the Helmholtz free energy is that F, as temperature approaches 0, is just going to be the thermal energy of our lowest possible state, where we're talking about the lowest possible state of our largish system over here. All right, so then the question is, does this approach the lowest possible state of our system? Well, that F tilde, again, it's minus kt times the logarithm of the partition function. So that's minus kt times the logarithm of a sum over all of the possible states of the system of e to the minus u of that state, energy of that state, over kt. So it is the sum of all the Boltzmann factors. And as temperature approaches 0, all of these Boltzmann factors are going to approach 0. They're all going to be sort of wiped out exponentially. But if we think about it, as the energy of the state goes up, that Boltzmann factor is going to be suppressed faster, and the Boltzmann factor that is suppressed the slowest will be the Boltzmann factor that corresponds to the lowest available energy state. So in other words, U0. And this sum then, as temperature approaches 0, that sum was just going to truncate to we're going to have minus kt times the logarithm of not a sum, but just e to the minus u0 over kt. That's the term out of this sum that will survive the closest as we approach absolute 0. And then that allows us to take the limit here and go kt. This is going to be log of e, so that's just going to be minus u naught over kt. And now the kt's will cancel, the minus signs will cancel, and then yes, indeed, the behavior as t approaches 0 of our guess for the Helmholtz free energy does in fact give us the correct form for the energy. So yes, this guess right here, that the Helmholtz free energy is just minus kt, or is minus kt times the logarithm of the partition function, does indeed seem to be borne out by our analysis here. And this then allows us to glue the quantum mechanical statistical thermodynamics, the quantum mechanical statistical mechanics of Boltzmann to the larger framework of classical thermodynamics, because now we can do things like calculate entropy is minus df dt, holding volume and number constant, and that pressure is minus df dv, holding temperature and number constant, and that chemical potential is plus df dn, holding temperature and volume constant. So we can get back to macroscopic thermodynamic quantities, classical thermodynamic quantities, but connect them right back to the partition function here, which then glues us straight onto our quantum mechanical model for our system. So now we have a way to go from the quantum mechanical model of the system through the power of these Boltzmann statistics to classical mechanics or classical thermodynamics kinds of quantities, and glue it to the kinds of stuff we were doing back in chapter 5. All right, well, before we move on to the next step here, let's go back and introduce one more idea about the partition function that'll be totally relevant to where we're going next here. And this idea is, what do we do when we have a composite system of, say, for instance, multiple different kinds of particles, or just multiple particles, which we want to try and build a partition function for a system of multiple particles. So to begin with, to be concrete again, let's consider a system of two particles which don't interact with each other. And so the energy of our two particle system is just going to be the energy of particle 1 and the energy of particle 2 added together. And so the partition function for our two particle system is going to be a sum over all of the states, and by states here we mean two particle states, of e to the minus beta times e1 of that state plus e2 of that state. Again, the state S here is a composite state of both of the two particles. So it's the state of our two particle system, not an individual single particle state. Well, we can break this up into the sum over S of e to the minus beta e1 of S times e to the minus beta e2 of S. Now, if our particles are distinguishable from one another, right, so the two particles are different kinds of particles, then we can actually break up these states into individual states for each particle, and this single sum then becomes a double sum. So it becomes the sum over all the states of particle 1 times, and then the sum of over all the states of particle 2 of e to the minus beta e1 of S1 and e to the minus beta e2 of S2. So because we can tell the two particles apart, we can describe our two particle system not by the state of just both particles together, but we can describe it as a double sum over all of the possible states for particle 1 and all of the possible states for particle 2. And indeed, we can break these sums apart. So the sum over S1 of e to the minus beta e1 of S1 and the sum over S2 of e to the minus beta e2 of S2. And this here, that's just z of particle 1, and this is z of particle 2. So we can take our total partition function here and say that it is the sum, or the product, of the two individual the partition functions for the two individual particles. So this is for two non-interacting. And the non-interacting came in here. If there was interaction, then we couldn't just add the individual particle energies together, because there would be an energy of the particle-particle interaction. Non-interacting distinguishable particles. And the distinguishable was important because that allowed us to break the sum into two different parts. If they were indistinguishable, then this double sum here that we just did would be double counting in the usual way that we have double counting for these things that we've run into multiple times. If we can't tell the particles apart, then a particle over here and a particle over here, 1, 2, is the same as 1, or 1, 2. And so we've double counted in this case by exactly a factor of 2, so that for indistinguishable particles, our total partition function would be half of the previous one. This would be 2 still non-interacting, but now these are indistinguishable particles. And we can kind of see how this is going to go if we keep adding more and more particles. So if we had n non-interacting distinguishable particles, so the result of n non-interacting distinguishable particles would be a z1 times a z2 times a z3 and so forth and so on up to z to the n. So this is n non-interacting distinguishable particles. Okay. And if they're indistinguishable, then instead of a factor of a half, well, we'd have a factor of a half for 2 of them. If we have 3 of them, we'd have a factor of, well, we'd still have that double counting for a factor of, or for the second and the third, but for the first we would have a triple counting, so we'd have 3 times 2, and in general, as we've seen before, the correction factor here for non-interacting indistinguishable particles would be 1 over n factorial to get rid of all of the multi-counting. And since the particles are indistinguishable from one another, instead of having n different partition functions, we've only got one partition function to the nth power. So this is n non-interacting indistinguishable particles. Right? So this then is how we combine systems where we've got a whole bunch of non-interacting particles that are the same types. And the sort of poster child for a system consisting of non-interacting particles of all the same type would be our model, again, of the ideal gas. So what we're going to do now is investigate the ideal gas. So let's take the result that we just built, that for a system of a large number n identical non-interacting molecules, the partition function is going to be 1 over n factorial times the single molecule partition function to the nth power. The energy of a state of a single particle or single molecule in our ideal gas, well, there's going to be some translational kinetic energy related to that state, plus some form of internal energies related to that state. And the internal energies here, we could be talking rotation, we could be talking vibrations, we could be talking electronic transitions. So we could be talking different energy levels, we could be talking or excited states and ground states, we could be talking vibrational motion of the molecule or the atoms and the molecules, we could be talking the molecule is rotating around its center of mass. But all of these we're just going to fold in under the interior energies, the energy associated with interior forces in our molecules, so that we can sort of break up the interior and translational motion. And so then when we build our Boltzmann factors, e to the minus e of the state over kt, that's going to be e to the minus translational energy of our state over kt times e to the minus internal energy of our state over kT. And thus we can build our single particle partition function is just the product of our translational partition function times our interior partition function, where we've defined here the translational partition function is the sum over all the translational states, e to the minus translational energy of our translational state over kT, and the interior partition function is the sum over all the interior states of e to the minus energy interior of our interior state over kT. All right, so let's look at what the partition function for translation for a molecule in some sort of a container might be. And in particular, what we're going to use is the classic quantum mechanics particle in a box. So in one dimension, a one-dimensional particle in a box So in a one-dimensional particle in a box, what we have is that we have some sort of a barrier at two ends of a cavity here. Our particles aren't allowed to penetrate the barriers, which are separated by some distance L, and so the only wave functions that our particles are able to have are those that give us standing waves with an integer number of antinodes. So the lowest fundamental frequency or lowest fundamental wavelength would be this one, which gives us half a wavelength between the two barriers. The second or first overtone would give us a full wave between the two barriers. The second overtone would give us 3 antinodes or a wave and a half between the two barriers, and so on. And so the quantum mechanically allowed states are standing waves with wavelengths of 2L over n, where n can be 1, 2, 3, and so on. Now, standing waves can be interpreted as a superposition of traveling waves traveling in opposite directions with a momentum given by the de Broglie relationship, that the momentum here then for each n state is Planck's constant divided by our standing wavelength. In other words, Planck's constant times the number n, our quantum number n, over twice the length. And so that's the momentum of our one-dimensional particle in a box, or our particle in a one-dimensional box. To turn that into a kinetic energy, the energy of that state is just p squared over 2m. So that's going to be Planck's constant squared, quantum number n squared, over 2 times 2 squared, that's 8, L squared m. And so those are the energies, the energies of our states quantized by quantum number n is this business here. So then our one-dimensional single particle partition function will be the sum over all those different n's of e to the minus energy of n over kt, and that's going to be the sum over n of e to the minus Planck's constant squared n squared over 8l squared mkt. Now, unless either the cavity size is very small or the temperature is very, very near absolute zero, we can approximate that the n's will be small compared to the cavity size, and so that the available so that this sum then can be approximated as an integral, and so we're going to approximate this as, again, the integral from 0 to infinity of e to the minus Planck's constant squared n squared over 8 ml squared kt dn. We're integrating over quantum number n from 0 to infinity. This is a familiar form. We can write this in the form of a Gaussian integral. If we let x squared equal this mess up here, n squared times h squared over 8ml squared kt, which means that our x here is n times the square root of h squared over 8ml squared kt. And if we turn that around and solve for n, then is x times the square root of 8ml squared kt over h squared, and our dn then is dx times the square root of this 8ml squared kt over Planck's constant squared, and therefore plugging these things back into our integral, our one-dimensional single particle partition function is the integral from 0 to infinity of e to the minus x squared times dx times this 8 square root of 8ml squared kt over h squared, and we can pull the big ugly constant out front. So this is the square root of 8ml squared kt over h squared times the integral from 0 to infinity of e to the minus x squared dx. Now that's almost the Gaussian integral we solved before. We solved the integral integrated over the interval from minus infinity to plus infinity, and since the integrand here is even, then this is just equal to 1/2 then the integral from 0 to infinity of e to the minus x squared dx is just going to be equal to 1/2 the integral from minus infinity to infinity of e to the minus x squared dx, which is, well, this integral was root pi, so this is going to be root pi over 2 is that integral, and therefore our partition function for our one-dimensional single particle in a box is going to be root pi over 2 times square root of 8ml squared kt over h squared. The 2 we could pull 4 from the 8 to make a 2 out here, which will cancel with this 2, and that's going to give us just a 2 in the middle, or in the radical, and we'll pull the pi back into the radical, so that gives us 2 pi mkt over h squared, and we'll pull out the L factor, and we're going to call this length over a quantity LQ, where this quantity LQ is defined as Planck's constant divided by the square root of 2 pi mkt. This is what our author calls the quantum length. It's basically the number of de Broglie wavelengths that you could stuff into our cavity. So in other words, it's something like the number of particle waves that you could stuff in here, or the number of particles you could stuff, number of places you could put a particle in that space. All right. So we just worked through that for one dimension. Our particle in a box is probably a particle in a three-dimensional box. So in 3D, we're going to have 3 p squared over 2m, px squared over 2m plus py squared over 2m plus pz squared over 2m. So the energy associated with the x, y, and z components of momentum, which means that our translational partition function for a single particle here is just going to be the sum over all the energy states, which in this case we're going to sum over x, y, and z. So we'll have an nx, an ny, and an nz of e to the minus, again there's going to be an h squared, x squared over 8 m lx kt, and an e to the minus h squared y squared over 8m ly squared kt, and etc., minus h squared z squared over 8 mlz squared kt. And this is just going to give us the same answer we had before, Lx over L quantum times Ly over L quantum times Lz over L quantum, or the volume divided by another quantity, which we're going to call the quantum volume, where VQ is just LQ cubed, and that's going to be H over square root of 2 pi mkt cubed. And this single particle translational partition function then would correspond to the number of de Broglie cubes you could stuff into a volume V for particles of energy kT. And then our single particle partition function becomes V over Q, or V over V quantum times whatever the partition function for our internal energy is. And if our particles are indistinguishable from one another, then our total partition function is just 1 over n factorial times this v over v quantum z interior to the n. So there is the partition function for n identical particles, identical non-interacting molecules in our three-dimensional volume. Since we're going to use it a bunch, let's go ahead and evaluate the logarithm of our partition function. That's going to be, well, logarithm of 1 over n factorial plus, we can pull down the n here, n times the logarithm of our volume plus the logarithm of our interior partition function minus the logarithm of our quantum volume. And we can use, this is going to be minus logarithm of n factorial plus, again, n log v plus log z interior minus log quantum volume. We can use Stirling's approximation here, assuming that the number of particles is large. So minus n log n plus n plus n times all the stuff in there. And we combine all the things that are multiplied by n here. So log z is n times log v plus log z interior minus log n minus log of quantum volume, and then plus 1. All right, and so that's the logarithm of our partition function. All right, now this is where the fun begins. We've done the hard work. We've evaluated the partition function for our quantum system. We've gone ahead and made or calculated what the logarithm of that partition function would look like. Now we can do things like, well, let's calculate the energy in our system. Energy is just minus 1 over z, 1 over the partition function, dz d beta. So that's going to be minus d by d beta of log z. So just evaluating this backwards. Well, the derivative of log z here well, let's look at what depends on temperature. Our internal partition function here, right? Our internal partition function, that's definitely a function of temperature. And what else is a function of temperature? Well, our quantum volume is a function of temperature because our quantum length here is a function of temperature. So of these terms, the z interior term and the quantum volume term terms are functions of temperature, but none of the other terms are functions of temperature. So this energy here is going to be minus n, right? So minus n times the derivative with respect to beta of log z interior. And then the quantum term, that's negative, so that's going to be plus n times well, that's going to give us a 1 over VQ, the derivative of logarithm of VQ, times the derivative of VQ with respect to beta. This term over here in the front, That's just n times the average interior energy of our particles. And this other term, this is going to be n. Well, let's hang on. To evaluate this other term, let's look at our quantum volume here a little bit. So our quantum volume VQ is some horrible ugly constant times kT to the minus 3/2. So we have some horrible ugly constant times kT to the minus 3/2. Or in other words, our quantum volume is that horrible ugly constant times beta to the 3/2. So the derivative of VQ with respect to beta is just going to be 3/2 C beta to the 1/2, which if we is 3/2. It would be nice if we could get this back in terms of the quantum volume. Well, that's 1 over beta times C beta to the 3/2. So that's 3/2 times 1 over beta times our quantum volume VQ is dVQ d beta. So we can plug that in over here. So this is n times 1 over our quantum volume times 3/2 1 over beta times our quantum volume. Those VQs cancel. And our energy then is n times the average interior energy of our molecules. That's intuitive. Plus n times 3/2 1 over beta, and beta is 1 over kT. So this is n times E interior plus 3/2 nkt, and there it is, our good old expected result. This is the familiar bit, and this bit over here is an entirely intuitive addition that we add all of the particle, or the number of particles times the average interior energy of the particle. In other words, that this 3/2 nkt is the translational kinetic energy of our system, and that the rest of our system's energy is stored up as interior energy in the particles. We could take the derivative again, obviously, with respect to temperature. If we wanted to calculate CV, that would be du dt, and that's going to give us a term due to the interior energy of our particles plus 3/2 nk. So there's a constant portion of the heat capacity due to translational motion, and then other terms come in when various internal degrees of freedom become available. Typically at lower temperatures, this is probably going to be rotational motion. As you increase the temperature, you'll get vibrations. As you increase the temperature beyond that, you'll get electronic transitions and so on and so forth. We could calculate the Helmholtz free energy of our ideal gas. That's just minus kT times the logarithm of our partition function. So that's minus nkt times the logarithm of our partition function from over here. Or it's minus kT times the logarithm of our partition function, which was n times log v plus log z internal minus log n minus log of the quantum volume plus 1. And we could write this as minus nkt times logarithm of volume minus logarithm of n minus logarithm of quantum volume plus 1. So all the terms except the z interior term, which we could then write as plus the Helmholtz free energy associated with those internal degrees of freedom, with those internal motions. We could then say the pressure, which is minus df dv, well, that's going to be plus nkt times, well, what depends on the volume here is this volume. What depends on the volume here is this volume term. So d log volume dv. None of the other terms explicitly depend on volume, and so this is nkt over v equals pressure, or in other words, we've rederived the ideal gas law. Check. All right, hooray. We could also use the Helmholtz free energy to derive things other than pressure, right? We could derive the entropy of our ideal gas. So S, the entropy, is minus df dt, and so that's going to be d by dt. The minus sign goes ahead and cancels out the minus sign of the Helmholtz free energy. So this is nkt, and again we're going to have logarithm of v minus logarithm of n minus logarithm of quantum volume plus 1, and minus f interior, again because the minus sign propagated inside. So that last term here then becomes minus df interior dt, or essentially the entropy associated with those interior degrees of freedom. Woof. Again, let's see, our quantum volume is h squared over 2 pi mkt to the 3/2, it's 2 pi up there, is some ugly constant times t to the minus 3/2. So the log of our quantum volume is going to be minus the logarithm of c times t to the minus 3/2. And we can break that into minus the logarithm of our constant c plus 3/2 times the logarithm of temperature. So we can plug that back into, we can plug this back into our entropy here. So entropy is d by dt of nkt times logarithm of volume minus logarithm of number of particles minus logarithm of big ugly constant plus 3/2 times the logarithm of temperature plus 1. And then dangling on the outside, we're going to have that entropy of the interior particles, or the interior degrees of freedom. And so this is d by dt. We can go ahead and combine a few of these pieces. nkt, logarithm of v over number of particles times c. So we're going to take these three things, none of which have any temperature dependence. N doesn't have a temperature dependence. Quantum, or C doesn't have any temperature dependence, and volume doesn't have any temperature dependence. So we can fold all those into this term here, plus a term 3/2 logarithm of temperature, obviously temperature dependent. And then our one term in here. And we keep this constant term around because all of these terms are multiplied by the n on the outside, or the t on the outside. And again, out here dangling at the end, the entropy associated with our interior degrees of freedom. And so now we're going to break this up. We're going to go ahead and distribute this nkt into the bits of the interior. So this is going to be d by dt of nkt log of v over nc plus 3/2 times the derivative of nkt log t plus the derivative of nkt multiplied by 1 in there. And again, our interior entropy sitting down at the end. So this first term is trivial. It's just d by dt of t times nk, leaving as an nk logarithm of v over nc. This second term we have to evaluate via a product rule. So v 3/2 nk times t times 1 over t. So that's this times the derivative of that, plus this times the derivative of t, so that's just log t. And the derivative of that is again trivially nk plus our interior entropy. The two temperatures here cancel each other out, and so we've got nk logarithm of v over n minus nk logarithm of c. I broke the c out of this logarithm because we're going to merge it back with the temperature thing here in a moment, plus nk times 3/2 log t plus 3/2 nk plus nk plus our s interior. So this here gives us 5/2 nk, and this term here gives us minus nk logarithm of the quantum volume. And so plugging this all together, what we get is that our entropy is nk times logarithm of v over n quantum volume plus 5/2 plus entropy associated with interior degrees of freedom. All right, and then finally, so we calculated energy, we calculated Helmholtz, or we calculated specific heat, We calculated the Helmholtz free energy. We used the Helmholtz free energy to calculate pressure and get us recover the ideal gas law. We used the Helmholtz free energy to calculate entropy, and got something that looks a bit reminiscent of the Sackur-Tetrode equation. And we can calculate the chemical potential here as dF dN, holding temperature and volume constant, and that's going to be d by dN of, again, our Helmholtz free energy minus nkt logarithm of v plus logarithm of z internal minus logarithm of n minus logarithm of the quantum volume and plus 1. Let's go ahead and break this up into some smaller pieces. So this is d by dN of minus nkt log volume plus d by dN of minus nkt log z internal plus d by dN of nkt log n. And so that's those first three terms. Then we have the quantum volume term, so plus d by dN of nkt log v quantum. And then finally the one term at the bottom, plus d by dN of just minus nkt. So we distributed the nkt and the derivative across our various terms here. And now we can start evaluating them bit by bit. All right, so this first one, the only n dependence is in the constant in the front. So this just gives us mu equals minus kt logarithm of volume. This term here, well, this we could call, again, the interior Helmholtz free energy. And so that term is plus dF interior dN. This third term is going to have, we're going to have to use the product rule here. So this gives us a nkt, this first times the derivative of the interior of the second there, which is just 1 over n, plus the second log n times the derivative of the first, which is just going to be kt log n. This, again, the only n dependence is out there in the front, so this is going to be plus kt log quantum volume, and the only n dependence here is the n there, so minus kt. The n's are going to cancel there, and that's going to give us a plus kt and a minus kt, and those are going to cancel. And so what we're left with is that our chemical potential here is minus kt times the logarithm of volume minus n and minus vq. So that's volume over n and quantum volume. So that's this term, and that term, plus our dF interior dN. Now let's go ahead and unpack this dF interior business again. So that's minus kt logarithm of v over n quantum volume, and plus d by dn of minus n kt logarithm of z interior. Obviously, there's n dependence out here. The partition function for the interior degrees of freedom, however, can't be dependent on the number of particles, because by the nature of interior degrees of freedom, these are forces that are interior to the molecule, not forces between molecules, so it can't depend on the number of molecules. So the only n dependence here is this one, and so this just gives us a minus kt times the logarithm of v z interior over n and the quantum volume, and that is the chemical potential of our ideal gas. All right, so what we've been able to put together here in Chapter 6 is starting with the Boltzmann statistics and the Boltzmann factor and the idea of the partition function. The partition function then becomes sort of the stand-in for entropy in many ways, and allows us to calculate a free energy, and then we can do the kinds of things we were doing in Chapter 4 and Chapter 5 with those Helmholtz, or with the Helmholtz free energy. Where we're going to go next in Chapter 7 is that we're going to relax the restriction that we weren't allowing particle exchange between our system and its environment, and we will look at the Gibbs free energy in the context of these Boltzmann-like statistics, and we will build up a new set of statistical mechanics that can be applied to the Gibbs free energy and particle exchange, and then we will have the full connection back to the Chapter 5 classical thermodynamics, but built up from a fully quantum mechanical modeling standpoint. All right, that's where we're going next.